Hi guys, welcome to the lesson of partial differential equations. So in the class, we are going to start applications of Fourier transforms, and we will see how to solve partial differential equations using Fourier transformations, right? So applications of Fourier transformations, we are going to start today, and let's talk about the basic pair of Fourier transform. So what actually is Fourier transform? That if we have a function given a function of x and we want to apply Fourier transformation on the function. So what we need to do is simply we need to integrate the function from negative infinity to positive infinity with the product of exponential to the power negative complex omega x dx, right? Where this a to the power negative iota omega x is called the kernel of Fourier transformation, right? So it's kernel of Fourier transformation. Now, as we know that if we apply this transformation, if we integrate this function, then we are uh, obviously going to get a function in terms of this omega, right? Because when we are going to integrate this function and apply the limits, then this x will be vanished because of the limits. Then the function that we'll get will be simply in terms of omega. So we can say that the Fourier transform of function of x is simply a function of omega, right? We can write in this way. And vice versa, we can write the Fourier inverse transformation of this function of omega. It will be f of x, right? When we will apply the inverse transform to this function here, then we are going to get this f of x back, right? Okay, so now for partial differential equations, for instance, if we have derivative like this dou u over dou x, and if we want to apply the Fourier transformation on this derivative, then we have to integrate this from negative infinity to positive infinity with the kernel of the transformation, that is exponential negative iota omega x dx, right? And now we can see that these are two functions, this dou u or dou x and this function. We can apply the product rule for integrals. And when we apply the product rule for the integrals and keeping this as a second function and keeping this as the first function, then we are going to get e to the power negative iota omega x times, now this is the derivative, the dou u or dou x. When we will integrate this, we are going to get this u of x simply, right? And the limits are from negative infinity to positive infinity, then minus integral again, the derivative of this exponential function. It will be negative iota omega e to the power negative iota omega x times u of x. All right, and dx, and again the limits from negative infinity to positive infinity. Now see here, the limits are from negative infinity to positive infinity. So the function u of x, whatever the function is, it's going to be zero when the limits are going to plus minus infinity, right? So the function is bounded and should have a bounded solution. So it's going to zero. It means that this whole term will become zero. So here we can write zero and then negative, negative, positive. We can bring out iota omega, and inside the integral we can write negative infinity to positive infinity e to the power negative iota omega x times function of x dx. And we already know that we can call this integral as a function of omega. We already talked about it in the beginning. So we can write it's iota omega times a function of omega, or just simply we can write u of omega because we are representing the function for x with u. So we can write it's u of omega. That means that is function of omega, or simply we can write iota omega u. So the Fourier transformation of dou u over dou x is simply equals to iota omega u. And this is the complex Fourier transformation for this dou u or dou x. Now let's talk about dou squared u over dou x squared. What will happen if we apply the Fourier transformation? So in the similar fashion, we can proceed this example that dou squared u over dou x squared times exponential iota omega x with negative sign. We are again going to integrate this by using the product rule, because we have two functions here. One function is this, one is this. And when we apply the integral here, so what will happen? This function remains as it is. Then times, now if we integrate dou square u or dou x square, we will get dou u over dou x. And again, the limits are from negative infinity to positive infinity, and minus again negative infinity to positive infinity. The derivative of this exponential function will be negative iota omega exponential to the power negative iota omega x times again dou u over dou x dx, right? Now we can see here that again this thing will become zero because the limits are from negative infinity to infinity as the solution is bounded. So this derivative should reach zero as this x reaches negative or positive infinity. So this term becomes zero. So it's now easier. So this negative negative is positive. We can bring out iota omega. Again, we can integrate negative infinity to positive infinity e to the power negative iota omega x times dou u over dou x dx. But this thing we already solved here. And what we get was iota omega u. So we can just simply substitute iota omega times iota omega u. So we are going to get iota omega squared times u, which will give negative omega squared u. So the Fourier transformation of dou squared u over dou x squared is nothing but it's simply negative omega squared u. Right, and similarly, if we want to proceed for dou cube u over dou x cube, that is the third partial of u with respect to x cube x, then we are going to simply integrate it from negative infinity to positive infinity, and doing the same thing for this e to the power negative omega x dx. So what we are going to get here is again this function will remain here as it is, and times this will become dou square u over dou x square from negative infinity to positive infinity minus negative infinity to positive infinity negative iota omega e to the power negative iota omega x times dou squared u over dou x squared dx, right? So again, this thing here is going to be zero because of these limits. So dou squared u over dou x squared is going to zero as the function x is going to plus minus infinity. Therefore, this will become iota omega times negative infinity to positive infinity dou squared u over dou x squared times e to the power negative iota omega x dx. And this thing we already computed here. And we have seen that this is negative omega squared u. So we can write it as uh, negative iota omega. Sorry, it's iota omega here. This is iota omega. So iota omega in place of iota omega. And then we have negative omega squared u. So this will give us negative iota omega cube u. So the Fourier transformation of Dava cube u over Dava x cube is nothing but it's simply negative iota omega cube times u, where this u is now function of omega and or you can simply say if it was initially function of x, then it's function of omega, right? So actually it's partial derivative, so you might get confused that why we are using only one function. So you can write it as omega comma t or something like that, if we will see in terms of heat equation when we will be using these transformations, right? So in general, how can we write this in general, right? So let's see. In general, we can write Fourier transformation of Dawa n u over Dawa x n. So it will be simply iota omega to the power n times u, and where this u is a function of omega, right? So in general, we can write in this way. So now it's easier if this problem arises anywhere, we can just simply apply the Fourier transformation here, and we can write this is simply this thing, right? So it's actually mm, let's see what happened here. It's negative, positive. Okay, something seems messy here. Let me check. So we see in general how we can write this transformation for partial derivatives, and then we have transformation of Dawa u over Dawa t. Simply, if we know that u is a function of x and t, for instance, then we have two partials in the equation, that is one with respect to t and one with respect to x, right? So if it's with respect to t, then what we need to do is again the same thing, from negative infinity to positive infinity. We are going to integrate this derivative with negative iota omega x dx. Okay, so now this partial is with respect to Dawa or Dawa t. So we can simply remove. Now let's see here first. We can write this as the operator, because this Dawa or Dawa t is the operator, and this u is simply a function of x comma t, for instance. Similarly, as in the previous case, it was a function. We only write it as function of x in the previous case, but it's actually not a function of x because it's partial. So it's a function of x with some other variable, right? So it might be a multivariable, in two variable, three variable, so any thing. So if it's u of x comma t exponential negative iota omega x dx, then we can simply exchange these operators, the integral and the differential operator. So we can move this operator outside, and this will be negative infinity to infinity u of x comma t times e to the power negative iota omega x dx, and this we already know that this thing is nothing but it's simply, it will be a function of omega, right? So we can write now, we can write it will be simply du omega t over dt, or we should write not in this manner. In fact, we should write in this manner. So this represents that this u is function of omega. Now it's not the function of x, right? So it has been transformed. So Fourier transformation of Dawa u over Dawa t will be nothing but it will be du over dt. Okay, so we can now journalize this term. If we have f of Dawa n u over Dawa tn, then it's simply dn u over dtn, right? So this is the generalization. And now let's take an example. Let's take a simple heat equation, and we will see how to solve the heat equation using the Fourier transformations. So, okay, let's start with a wave equation. So we have dou squared u over dou t squared equals c squared dou squared u over dou x squared. And the limits are infinite, so it's an infinite string problem. And we already discussed the D'Alembert's method for its infinite string problem, and now here also we will see that we'll get the same results as in D'Alembert's method, right? So Fourier transform will conclude and verify the result. So x comma 0, it's equal to x, so the initial displacement is 0. Sorry, initial velocity is 0. Initial displacement is given by a function of x. Applying the Fourier transformation. So apply the Fourier transformation on both sides of the equation. Again, we already discussed Fourier transform of this function. It will be nothing but d squared u over dt squared equals c squared times Fourier transform of this function. It will be iota omega squared times u. And then we are going to get a simple second order differential equation, that is d squared u over dt squared equals negative omega squared c squared du. Okay, so now what we are going to get by solving this problem is, we know this is a second order differential equation. You can write r squared is equals to omega squared c squared negative times. So r equals positive negative omega c with this little complex here, right? Because of the negative sign. So it's a complex root. So we can write u of omega comma t equals a cosine omega c t plus b sine omega c and t. Now, what we need to do is we need to apply initial conditions that are given. So the initial condition is u of x comma 0 equals f of x here, initial displacement. So first of all, we need to apply the Fourier transform to this initial condition, and then we can use these conditions. So it's simple. If you apply Fourier transform here, we will get u of omega comma 0. And on the right side, we already know we will get f of omega, as we discussed, right? So the Fourier transform of f of x will be nothing but f of omega. So we can simply write here that u of omega 0 equals a cosine 0 plus b sine 0 equals f of omega. So from here, sine 0, 0, so this implies that a equals f of omega. Now for b, the other initial condition is given, that is the initial velocity, and it's given that it's 0. So first of all, we need to take the derivative of the function. So ut, u with respect to t, ut will be equals to negative a omega c cosine c omega t plus, sorry, it will be sine, not cosine. It will be sine, and then uh, b omega c cosine omega ct. This equals 0 when it's omega comma 0. So it implies A times 0 because this sine 0 is 0 plus B omega times cosine omega ct. So it will be 1 because cosine 0 is 1 equals 0, which implies that B equals 0. So now the equation is pretty much simplified. The solution is only U equals f of omega cosine omega ct. Now this is the solution, but it's in terms of omega comma t, but we need the solution in terms of x comma t where we have started, right? So now for that we need to invert this problem. We need to apply the inverse transformation to the function. So apply inverse transformation to the u, and again for inverse transformation we need to do just one step, that is now this will become u of x comma t by inversion equals, now this thing we need to just integrate from negative infinity to positive infinity, and we can write f of omega times cosine omega ct times e negative, sorry, now it will be positive omega iota x times d omega. So this is the final solution of this problem, and we can further simplify this in a way that we can write this as we can write this thing here, this thing as Fourier inverse of function of omega times the apply the Euler's identity to cosine omega ct, so it will be the power negative iota c omega t over 2, and then if we further simplify this, it will be Fourier inverse 1 over 2. You can take it outside, so it will be f of omega times e to the power negative iota c omega t plus f of omega e to the power iota c omega t. And if we apply the linearity property of inverse transforms, so you can apply individual transformation to these two functions inside the bracket. So it can be written like this, plus Fourier inverse of f of omega e to the power iota c omega t. So we know that now this thing here, this half, we can keep it outside, and this thing will be nothing but it will be a function of x plus ct, and plus this thing here, it will be a function of x, sorry, this will be a function of x plus x minus ct. This will be a function of x minus ct, and this will be a function of x plus ct. All right, so in this manner, we also verified our solution when we solved it using the D'Alembert's method for zero initial velocity. We get exactly this form of the solution. So, and this is also called the D'Alembert solution, ultimately. So we discussed a problem on this Fourier transformation for wave equation. Now in the next class, we will discuss some more problems, and we will discuss heat equation as well, the Laplace equation, and we'll discuss more problems in the next lesson. In this lesson, we already discussed some integrals and some basics of Fourier transformation. So that's all for the time being. Thank you for watching the lesson. Goodbye.